Hello everyone and welcome to another Würth Elektronik webinar. My name is Silas and I will moderate this webinar today. Our topic of today is Heatsink Solutions thermal management in our electronics devices. Our speaker today is Maria Cuesta. Hi Maria, cool to have you here. She is product manager in the field of EMC shielding and thermal solutions. So she will hold the presentation and after that will answer your questions. So now I will hand over to Maria and I wish you an exciting webinar.
Thank you, Silas. Welcome everybody to this webinar. Today we are going to talk about thermal management, but especially we are going to focus on the heatsink solutions inside this field. In the webinar, we are going to talk about why should we cool down our devices, how we can actually cool them down, some tips inside the heatsink design world, even though it's a really open topic, but we will go in deep into simple and basics of this heatsink design, and finally, what as Würth Elektronik we can offer inside our portfolio. So, why do we cool down our thermal or our PCBs? First, because it's not a topic that affects 1 out of 1,000 of PCBs. In fact, more than 50% of the times that a device fails is due to temperature challenge. It's due that we didn't handle thermal management in a proper way. So in order to have a PCB that lasts a lot of years in the optimal performance, we have to take into account thermal management from the earliest stage of our design. Temperature challenges can deal to mechanical failures because when we have a PCB, we have different thermal expansion coefficients. So when we are having this change in temperature and this stress on the devices, this can deal to also mechanical stress failure. And we are in the area of miniaturization. Electronics in the past were bigger PCBs, bigger computer, occupying a whole room. But right now, what we want is fast computers that are performing at their maximum capacity and during a really long time. So this comes with a really high power density inside a PCB, and without any doubt, we are going to have hotspots that are going to affect the performance of our design. Either we want to have a design that is working half of its capacity, so it's not heating up, or we deal with this challenge from the earliest stage, and then we can have our devices running at 100% of our capacity at the end. Inside the design phase, there is a lot of steps. When we are talking about thermal management, especially if we are talking about heatsinks, we have to take into account the heatsinks in our design from the earliest stage. Because imagine you are doing your PCB and you imagine that this is the ideal world in which we are not going to have any challenge, and then you arrive to the testing or even production phase. And in this moment, your layout is closed, you don't have enough time, you have to do a lot of investment if you want to do any change. So the solution that you are going to find from thermal management point of view is not going to be cost effective, and the design cost that you are going to have is quite high. So the sooner you get into account heatsinks in your design or thermal management in general, to be honest, the easier is going to be later for your performance in your devices. Okay, how we can cool down our devices if it's so important to do it? We have 3 ways of heat transfer. At the end, what we want is that all the heat that you are generating cannot be magically destroyed. So you want to transfer this heat from your device to the ambient, to the cooling device you have designed, anywhere that is not affecting the performance of your PCB. So we have 3 main ways of transfer. We have conduction, convection, and radiation. Conduction is the transfer inside 2 surfaces that are together. For example, a heatsink together with a CPU. Then we can conduct the heat from this hot component to the heatsink. This conduction, it's conditioned for temperature difference. So if my component is at 100 degrees and my heatsink is at 100 degrees also, there is not going to be any heat transfer. We have to have a temperature difference between them. Of course, we have to have a contact area. The larger, the better. You can see it in the formula. And also the thickness we talk is the air gap between my component and my cooling device. So the closer they are between each other, the easier the heat will transfer from your device to the cooling device. And the thermal conductivity, of course, is the ability of the material to conduct the heat. So how easy it's for the material to conduct the heat inside itself. The higher this value, the better. This is why normally, and we have included here some values for aluminum and copper, normally the heat sinks in the market are made either of aluminum or copper, because the thermal conductivity of these materials is quite high. Later we have convection, the typical user case. You are working with your computer and suddenly the fan of the CPU is starting to run. Basically, this is because the CPU is getting hotter, and then with this fan you can send a cold fluid, in this case air. So this is the principle for heat transfer with convection. You have a fan that is sending cold air, and then this cold air makes the temperature difference with your component. Apart, it's important the surface area, and in the formula you can see also the convection coefficient. This is a theoretical value, but that will differ depending on the situation. If you are in vacuum, no air, no fluid, so the value is going to be 0. Don't put fans if you are in this condition. If you are in natural convection, just your PCB and the heatsink, for example, the value is 1. And if you include a fan, depending on the characteristic, the size that you are using, and the velocity of the air, then the value can go up to 5, 10, 20, depends on the situation. And last but not least, it's the radiation. Radiation is a topic that we often don't talk too much or we don't take into account, but it actually affects how we design our heat sinks, for example. All bodies, if the temperature of the body is different from the temperature of the room, they radiate some heat. They transfer some heat to the ambient. So of course, this temperature difference has to exist. And also there is a key concept here that is the emissivity, the first value of the formula. The emissivity is the ability of a material to radiate heat. How easy a body can radiate heat. If you see in the table below, when we are working with polished aluminum or with raw aluminum, this value is almost 0, 0.04. But if we anodize this material, for example, black anodized aluminum, it's increased the emissivity up to 0.7, even up to 0.8. So we are talking that the maximum emissivity a material can have is 1, and just by anodizing the heat sinks, you can achieve this increase in the emissivity. So this is a key topic when we see in the market that a heat sink with the same design, it's working better in anodization, it's also because it's radiating more heat. Let's take a deep look in how we can design our heat sinks. But first, let's define what is actually a heat sink. A heat sink at the end is a passive cooling device that is designed to absorb and disperse heat by increasing the surface area available. What we were talking, if you want to dissipate heat in a CPU that is 2 by 2 centimeters or 1 by 1 centimeter, it's going to be almost impossible. You need the help of these devices to increase the surface area available. So here you can see represented in red arrows the heat transfer through conduction inside the heatsink. And also you have the blue arrows representing the radiation and the convection coefficient. So this is more or less how it works. In heatsinks, you have to use the 3 ways of heat transfer to help you to transfer the heat to the ambient. When we are talking with these pin-fin or fin heatsinks that are quite known in the market, the designer can take a look in 3 main things. First is the base thickness. The base is like the storage room for the heat. So the thicker the base, more material you have, and then more heat you can storage in the heatsink. Of course, with a limit. If you are using a base of 20 millimeters, then it's not worthy the investment, but the thicker normally, the more heat you can store, and also the more lateral spreading you can achieve. Of course, the disadvantage, let's say like that, is that the thicker, the heavier the heatsink, and also normally more expensive because you are using more material. So as a rule of thumb, let's say that if your thickness is 1-2 millimeter thickness, normally this heatsink is focused on low power application. So for example, 5 watts, 6 watts below these values. And for other general or high power applications in the range of 3 millimeters. Also, usually the bigger the heatsink, the thicker the base. It's proportional. Then we have the fin thickness. The same, if my fin is thicker, I can storage more heat, I can conduct more heat, and then I can radiate it to the ambient. But imagine that I have a heatsink that is 10 millimeters length. The thicker I put the fins, the less fins I can put. So it's a compromise between how many fins I want to have in my design and the thickness I can put in all of them. As a rule of thumb, to give a tip, below 0.5 millimeter thickness, we say that this heatsink is focused in forced convection environments, and over 1 millimeter thickness is for natural convection. Again, I want to point out something here. It's not that if my heatsink is 0.5 millimeter thickness, then I have to put a fan. I have to be in forced convection environment. No, these are tips that when you dimension your heatsink, you put your application and suddenly you start running and see that something is wrong, something is not matching. Then you can start thinking, okay, should I increase the base of my thickness, the thickness of my base? Should I increase the thickness of my fin? These are tips, and then you can take a look at them and do the changes. But it's not that mandatory, I have to do this if this is the characteristic of my heatsink. And last, we have the fin separation. So this will determine how the air flows between these fins. What happens between the fins is that it creates a thermal boundary layer. So it's a region in which the air temperature changes from the temperature of my heatsink, that in theory is super hot because it's dissipating heat, and the temperature of the ambient. If you see in the top part of the heatsink fins, the thermal boundary layers are not touching. So there is temperature difference, which, if you remember from the slide, is key to have heat transfer between the component and the ambient. But what happens with these thermally boundary layers overlap? That I lose this temperature difference between them. And then I'm having an issue. I cannot conduct and radiate the heat as good as I would like. So there are solutions. What can we do if we are in this situation? Either we separate the fins more, so we avoid that the thermally boundary layer overlap, or we include a fan. In this way, the fan is going to reduce the thermally boundary layer between the fins, and you are not going to deal with this challenge. It's possible to calculate with a lot of formulas how is the thermally boundary layer, how thick is this thermally boundary layer, but normally the approach is either simulate the heatsink solution and later test it to check if actually it's working or not. If we have to give a rule of thumb, between 2 to 4 millimeters separation between the fins, we are in forced convection environment because the fins are closer between each other, and over 5 millimeters separation, we are in natural convection environment, if we want to be in the really safe side with this topic. As a summary, it conditions a lot the design of your heatsink if you are in forced or natural convection environment. If you are in a forced convection environment, obviously you have a higher cooling capacity. The cooling performance can be controlled dynamically because you can choose when the heat with the fan is on or off, and it enables smaller heatsinks due to the help of the fan. But you're going to deal with a lot of noise, dust buildup, it's more expensive normally, and an extra space for the power consumption of the fan. Normally, if I have to say something, I will recommend to try to work in natural convection environment. Maybe you have to invest in a bigger heatsink, in a more expensive heatsink, in a better thermal interface material, but at the global point of view, normally the costs are lower, the energy consumption is lower, and also you are occupying less space, because even if the heatsink is bigger, then you are not going to need a fan and a power administration to this fan. So again, it's a compromise, depends on the application. You can find both solutions, and both of them have advantages and challenges. Okay, but if we are talking about heatsinks, it's impossible to not talk about thermal interface material, how we are going to connect properly the cooling device we are choosing with the component that we want to cool down. A thermal interface material ensures good thermal transfer between this heat source and the colony assembly through conduction. So a lot of times we have seen customers that they are using a pretty nice heatsink, really good thermal solution, a cool fan, and they are saying, but something is wrong, something is not working as I expected. Normally, we underestimate the power of a good thermal contact between this heatsink and the component, because if we are not having a almost perfect contact between both surfaces, then you are not going to have this heat transfer that you are expecting from your component to the heatsink. So really investing and taking into account to include a thermal interface material is key for the performance of the whole solution. In fact, you can, with more or less simple calculations, consider which type of thermal interface material you need for your application. So imagine that you're working with a component that the power loss is 2.5 watts, and then you know that the ambient temperature of your applications is 60 degrees, and you have a target temperature. Okay, my component cannot be hotter than 85 degrees, like in this example. Then you can do a resistor network, like you can see in the screen, and with a simple formula, you can calculate the resistance of the thermal interface material that you want. Because you have three sections: the junction to case, the resistance junction to case, that means the resistance from the component, and this value normally is on the datasheet. Then the resistance of the thermal interface material, that this is what we are calculating right now, and then the resistance of the heatsink. That it will depend on if we are on forced convection or natural convection environment, but that is also specified normally in the datasheets. So with this, with a simple formula, we get that the value of the thermal interface material, of the resistance of the thermal interface materials, is 1.3. If it's lower, then normally the temperature of my component will be also lower. If I'm choosing a material with higher thermal conductivity, thermal resistance, it will also mean that we will have higher temperature on the component. In this example, you can see that in the green side, we choose a thermal interface material with lower thermal resistance, and the junction value is below 85. And if we choose one with higher thermal resistance, the value will be also higher. Then what can we find in our portfolio? The objective of this is not to just say, okay, these are the heat sinks that you can find, because then it's easy to go on the website and check it. It's to actually understand why we choose these designs and how this can support your design. In our portfolio, from many years, we already have thermal interface material, but now we are approaching a further step for a whole and complete thermal solution, including the heat sinks. Heat sinks have millions of possible designs and also a lot of type of materials. But inside the material choice, we went between copper and aluminum that are quite common in the market. But for the first heat sinks that we have in our portfolio, we choose aluminum. Why? It's true that the thermal conductivity is not as high as the copper one, but it's pretty good and enough for a lot of applications. The density is lower, so you can find lighter heat sinks for the application, and also the price comparison between the same heat sink in copper and in aluminum. It's crazy how the copper one increased the price. Of course, depending on the application, on the solution, sometimes copper is the right choice, but for the first approach in our portfolio, we are working with aluminum heat sinks. And inside the designs, we focus more on applications, which applications we want to target. The first one is transistor application. So this is why HTO matchcode heat sinks for transistor, especially TO220, TO247 that are massively used in the market. We have 4 different topologies to adapt to different needs. The clip-on topology, it's a pretty simple heatsink. You don't even need to take into account when designing your PCB layout. You just put it inside the component and just press a little bit the legs and you clip it. So you save space, save money, you don't need a screw. But of course, from the thermal management point of view, if you want to dissipate 10 watts, this is not the heatsink that you should choose. But if you are in the range of 1, 2, 3 watts dissipating, then probably this is a really good approach. Then we have the simple topology, or straight heatsink fins. In this one, it's quite similar to the clip-on with a slightly better performance because you have more area, more surface area available, but you need to screw directly on the component. This heatsink is also possible to include it in your PCB in the last phase of your design because you don't need to include it in the PCB layout. The curve topology has pretty similar advantages to the simple topology, but due to this curve in the fins, you have more area available to dissipate the heat, and then the performance is also slightly better, occupying quite similar volume. Last, we have the big one, let's say it like that, that is the extruded heatsink. In this case, from the performance point of view, is the best one, but you have to take into account from the early stage of your design because you have two legs that have to be included in the layout. It occupies a lot of space. So if you are going to dissipate 8, 9, 10 watts, for sure you are going to go more in this direction than in the ones that I previously saw, but you have to take into account in the early stage of your design. Here is a comparison. I simulate a power in a TO 220 of 10 watts power dissipation, and you can see clearly the difference. The curved topology heatsink, the component is almost at 300 degrees, and the extruded one is at 120. Again, this is not a real case application, it's just an example to actually see the difference between both heatsinks in the same situation. We developed further this simulation and this comparison, and as you can see, in 1, 5, 10 watts, you have different options you can choose. At the end, it's a mistake to think, okay, doesn't matter how much I'm dissipating, I will go for the bigger, most expensive heatsink. No, you truly need to understand your application, your demands, your performance, and they say, hey, maybe I can go for the simple option, or maybe a slightly bigger, or a curved topology, or okay, I mean really high power application, let's go for the extruded one. If you understand what are your needs, then you have the power to choose between different designs with this criteria. We offer inside our portfolio also the mounting process. So we offer the screw, the nut to clip everything together, and also the insulating bushing. This is important because transistors are electrically conductive, and a lot of times you invest in a thermal isolator to isolate the heatsink from the component, but the screw is also touching the component. So if you don't isolate the screw from the component, you are going to have electrical conduction. So this isolating bushing that you are seeing on the screen is to isolate specifically the screw from touching the component and the heatsink. Later we have the HIC application, so heatsinks for ICs. And in this way we have two topologies, let's say like that, one direction and bidirectional, depending on how the air can flow inside the fins. If you are in a forced convection environment, you have clear how you want to place your fan and how it's going to be the airflow direction, then one direction heatsink is the choice for you. But if you are in a more open situation, you don't know if you are going to put a fan or not, or how the airflow is going to happen, then bidirectional heatsinks give you more freedom for a last-minute decision, let's say it like that. We have different sizes inside our portfolio, and the idea is to adapt to the main applications, so CPU, BGAs, Raspberry Pi, any type of applications that you can think of can be adapted to these heatsinks. A small break, let's talk about anodization. If you have realized during the whole presentation, all the heatsinks are painted in black. This is because they are anodized in black. So anodization is an electromechanical process that transforms this outer surface of the heatsink, and it gives a more durable surface. So as we talked in the past, this process increases emissivity, so increased radiation, makes the heatsink more durable and helps against corrosion. So it has huge advantages, and this is why normally we work with this type of heatsinks. And last but not least, we are talking about HTOI and HICI. So this type of match codes are exactly the same heatsinks we have talked about, but with thermal interface material pre-applied. This is more than a product, I will say a service, because in this way we are going to warranty an optimal performance. If you have your heatsink, you already have the thermal interface material, you warranty good contact, and then you just put it with your solution, having the complete package. In the case of the heatsinks for IC, we use thermal adhesive tape. In this way, you can have the good thermal contact and also the mechanical adhesion to the component. And in our portfolio, you can find the heatsink with the thermal interface material and also both of them separately. So either you can decide if you want to pre-assemble it or you already want it pre-assembled. The HTO1, the heatsinks for transistors, we have it with tins. Tins, it's our material that guarantees electrical isolation, which is key for this type of application. And again, you can have it already pre-assembled or both of them separately and do by yourself the pre-assembly. In case maybe you are wondering, do I really need the material pre-applied or not? You can test it by yourself and then decide which final solution you want. A final view of our portfolio and some extra information that I wanted to add before finishing the presentation. First is about thermal characterization. This is an important topic because when we go in the datasheet of a heatsink and we say, okay, what is the thermal resistance of the heatsink? And we say, okay, it's 21. And then the same heatsink, same design, also black anodized, you still look at another dataset, another manufacturer, and you say, oh, this one, instead of 21, the value is 15. Why is this different? Is because this one is better magically? No. The thing is, the reality is that there is not a standard way of characterizing heatsinks. So you can be characterizing a heatsink in a way that gives you a value, and later the same manufacturer, another manufacturer, characterize the same heatsink in another way. And then the value they put on the datasets is different. So how we do it, and we openly share also in our guidelines, is we have a heat source, we have thermal interface material and the heatsink, and also a fan. And we test our heatsink with the fan on and with the fan off to check force and natural convection environments. But this is not the real application of almost any PCB. When you are having a PCB, you have a lot of components, maybe you are in a closed environment, maybe you have 2 fans or 1 or non-fan. So at the end, this thermal value, it's a good reference to compare between datasets. Okay, this is 21, this is 15, this is 23. You can see the different designs and compare the values. But if you actually want to know the exact value that you are going to have in your application, there is no way any dataset can give you this exact value. Doesn't matter if it's done in one way or in another, it's impossible. So knowing this, you can use this value as a tool for you to, okay, I have more or less reference of which range of values I am moving, and then when I'm in my final application, I can do my own calculation, my own test, my own simulations, and get the final performance that I am expecting. We have also a support note, a guideline. We use it for more than saying our portfolio is to support you in the technical point of view. So how heat transfer works, which type of heat sinks we have, how they adapt to their applications, with which thermal interface material you can combine. And with these specifications, with this combination, we really want to give some inputs to the engineer. So it's a decision that you make with the knowledge and not just saying, okay, I need a heatsink because I want to cool down my device. I don't care how or why this is happening. And we truly think that in this way, you will be able to make a smarter, most efficient decision for your own application. I hope you have enjoyed. And if you have any question also, feel free to reach during the presentation or after.
So, thank you, Maria, for your interesting presentation. Now we'll come to your questions. Before we start with the Q&A session, I will share the handout from the presentation from Maria. So now you can download it. Okay, then I would say we can start with the questions. First question. Could you please talk about heatsinks and electromagnetic radiation in switching applications?
This will be a complete topic for a huge presentation. It's true that when you are working with a heatsink, a component, and then you are not grounding the heatsink, you can actually have some electromagnetic issues and capacitance creation in this process. But I will say that for this I will need a whole hour to explain it. So feel free to reach out to the email exchange if you have a specific question or case, and we can treat this topic in depth because it's quite wide.
Okay, thank you. Then next questions. The color of the heatsinks affects the performance?
I would say no. At the end, is if the heatsink is anodized or not, then this will increase or decrease the emissivity, the radiation capacity. And it's true that the black color normally is the most stable one. If you are in UV radiation applications, normally the color, it's more resistant to this type of changes. But from the thermal perspective, the color, I would say, does not affect.
Mm-hmm. Okay, thank you. Then next questions. Can you please comment on thermal cameras in testing heatsinks?
Okay, it's also An open question I will remark when testing any heatsink or putting thermal cameras is exactly what you want to measure. Because sometimes we are just putting a thermal camera and seeing the temperature of the heatsink, but you are not having any monitorization of the actual temperature of the component below. So maybe your heatsink is at 25 degrees and we assume, okay, this is the temperature of my component. And that's not necessarily the case. Because if you are not having a good contact, the heat is accumulating the component, your heatsink is not receiving this heat transfer, and then your component, your heatsink is really cold, let's say it like that, but your component is heating up. So my input with this question is, okay, take care of what's temperature you are monitoring and how.
Okay, thank you. Next question. How high thermal conductivity is the TIM?
This depends on the team you are talking. Thermal conductivity can go from 1 up to 6 watts, I think, in our standard portfolio. But of course, in the market, there are teams with 10 watts meter Kelvin or thermal pasted with values really high. It really depends on the thermal interface material you are using. And also, thermal conductivity is important, but it's also really important the thermal resistance, because I can have a material with really high thermal conductivity, but if I'm putting 20 millimeters of this material, the thermal resistance that I'm having is that high that does not compensate the high thermal conductivity I'm using. Sometimes it's worth it to reduce the gap the maximum as possible, and then maybe you can go to lower thermal conductivities, because also it really affects the price of the material depending on which material you are using. So, yeah.
Okay, thank you. Then, next question. Does Würth Elektronik have an online application section where we can do thermal designs using a thermal calculator if one exists within the Würth Elektronik app notes?
Right now we don't have it. We just have the heatsinks from 1 month and a half, 2 months, but we are working on it because it's true that it's a really useful tool, especially if you combine with thermal interface material, you can take into account both things and have the whole approach. So I hope it's coming soon, but right now we don't have it.
Then, next question. Which heatsinks of your portfolio are meant to be used with a fan?
Yeah, this is a common question, a really good question. A heatsink is not meant to be worked with a fan. The idea is that, okay, my application needs forced convection or does not need. Maybe I have a 20 by 20 millimeters heatsink, and if I'm using this size of heatsink, then I need a fan. Or maybe I say, okay, I use a 40 by 40 millimeters heatsinks, and then I don't need a fan because I increase the heatsink size. So I will not say that a heatsink it's meant to be used with a fan. I would say that depends on the application. You can compromise. Either I go for bigger heatsink, thicker base, thicker fins, or I include the fan and I can work with smaller versions.
Thank you. Then, next question. Take this one. What about surface mount heatsinks and the thermal paste to secure the component to the RHS?
I don't know if I understand right the question, but if you are meaning for these heatsinks that are soldered to the PCB, in the surface of the PCB, normally these heatsinks directly use the thermal bias to transfer the heat, and some of them even don't touch directly the component. And if it's directly mounted on the surface, for example, our HIC match codes, we pre-apply TTT, because in this way you guarantee thermal adhesion. But it's true that other options can be, for example, PCM. If you are using a heatsink with push pin, then PCM is a really good option because you normally can pressurize a little bit the material, or a gap filler, you can pressurize a little bit them thanks to the push pin. And in this way, you can use other type of materials that don't necessarily also have adhesive.
Thank you. Then, next questions. this one. What interface choose to connect a PCB to a heatsink with a gap more than 5 millimeters?
Okay, more than 5 millimeters, it's quite a gap. So PCM I will not recommend because it's for microscopical gaps when it goes to liquid. Tins, that is a material that we use for heatsink, is up to 0.2 millimeters gap. So I will go for TGF. TGF is a gap filler that for 5 millimeters range, it's quite good. If you pressurize a little bit, then perfect for the thermal conductivity, for the thermal resistance. And yeah, with this information, I would say TGF.
Then next question. Oh. It's a lot of questions in the chat, so
that's good.
Yeah. Is there a plan to enlarge our heatsink product portfolio soon?
Well, we are always growing and always searching for new products. So of course, it's in our plans to include more heatsinks inside our portfolio. Soon is a relative word, so I'm not brave enough to say soon, but it's something that for sure we are working. We have just started with the portfolio, and this is the beginning for sure.
Then next questions. Is TIM always mandatory between heatsinks and components?
I would not say mandatory. I would say highly recommendable, because when you want a good connection, even if they are directly together, you cannot guarantee without this thermal interface material or thermal paste or the solution you want to find. I will truly recommend, if you are investing your time, your money in your design to include a heatsink, that you include a thermal interface material.
Okay, thank you. Then next question. Is there a case where a lower thermal resistance is not desired in a TIM, or is it a blanket lower is better?
The theory would say the lower the better, but in real applications, it's not only about what is the best point of view theoretically, it's also about what is the best point of view for the application point of view. So maybe a thermal paste has a really low value in comparison with a thermal material, but then how you pre-apply it, how you put it in your in mass production to make it efficient. And then maybe you say, okay, I move from one part to another. Or maybe you say, okay, I have to complete 5 millimeter gap. This is too high. Instead of investing a lot of money in a really high thermal conductivity material with this big gap, I'd reduce the gap in my design, and I can go for cheaper thermal materials with lower thermal conductivities. So I would say it's a compromise. Not always the lower the thermal resistance, the better. There are other factors to take into account.
Thank you. Then next question. Is there any white paper on optimizing boundary layer thickness through passive convection techniques, such as using fins-oriented
orthogonally, I think.
Yeah, to the airflow.
Oh, wow. A specific question. I have read some papers. To be honest, I didn't go quite in deep about this topic, but of course, you can contact and we can share some of the papers I have already read. I'm sure that they have investigated about this topic.
Okay, thank you. Then I would say we have time for one last question. What about 3D printed materials to build complex dissipation plates, maybe with an embedded water cooling circuit? Würth has some option to do that.
Right now, we don't have some options to do that, but I think it's a quite nice thing to explore. 3D printed materials normally have lower thermal conductivity, so maybe the performance of the same heat sinks in 3D printed or in extrusion or other manufacturing techniques is 20, 30, 40% lower in the performance. However, for cooling, water cooling circuits, it can be also a really interesting option. And yeah, for simulation, for investigation, for real applications that other companies, of course, offer, I think it's really nice. But right now, we don't offer something in this sense.
Mm-hmm. Okay, perfect. Yeah, I see no more questions. But yeah, Maria will answer them later on via email in the next days. So thank you for your attention. I hope you enjoyed it. Maria, thank you for your time.
Thanks.
Yeah, hopefully we see us on our next webinar. Have a good day and bye-bye.